So hello, everybody. Welcome to the Atto Fridays. Our speaker today is Professor Alexis Chacon. He obtained his PhD at the University de Salamanca under the supervision of Professor Camilo Ruiz and Professor Luis Playa, specialized in the physics of electron wave packets characterization via attosecond quantum interferometry. His first postdoc was done at ICFO in the quantum theory group of Professor Levenstein, and afterwards he joined the LANL to investigate the topological phases and transitions of matter using nonlinear optical responses, in which Alexis joined to the SLAC SU, the theoretical experimental realization of featuring 3D topological insulators at the surface states was observed. And then between October 2019 and December 2022, he was a group leader at the Max Planck Institute in Korea, clearly South Korea. And then since January this year, he's a research professor at the group of Professor Yong-Won Kim at POSTECH University. And I met him actually a long time ago, and he also was present in the quantum battles in 2020 in the quantum interference panel. So feel free to start. We're ready to go.
Okay, let's start with sharing the screen. So as Carla, thank you very much, Carla, for this nice introduction. And today I will speak about ultrafast spectroscopy of topological materials via high harmonic generations. So most of the people already know my name. My name is Alexis Chacon, and then I'm working, as Carla said, at POSTECH University. So, oops. In high harmonic generation, I will be starting to talk in my outline. The first point will be in high harmonic generation in gases and solids, and why nonlinear optical spectroscopy today, and why now as well, through the theoretical proposal that we did on topological chair insulators, and the experimental realization of the topological proving of the three-dimensional topological insulators in bismuth-selenides with high harmonic generations. And finally, I will conclude and present my outlook. So when n strong, let's start with the gases. When with this particular high harmonic generation in gases. When the n strong infrared laser pulse is focuses into an atomic or molecular target gas in gas phase, high nonlinear processes occur in the material. And in this case, in the atomic and the molecular gas phases, due to these high nonlinear processes, we can observe as an output of high harmonic, as an output of this interaction, high harmonics in terms of the fundamental frequencies. High harmonics mean here that we observe harmonics not exactly between 1 and 4. We observe harmonic till even sometimes 100 harmonics of the fundamental laser. But here for just scratch of visualization of the example, here we can see the first harmonic, second harmonic, the third harmonic, and the fourth harmonic, and so on, that are produced by these processes independently of the symmetries of the system. And here, of course, is the dipole moment, which produce that radiations from a quantum mechanical point of view, and so on. And here is one of the first harmonic spectra done, presented by Anne, where here we have the intensity of photon signal, again the wavelengths of the spectra, and in the top axis we have the harmonic order. We can see huge enhancements of this harmonic emission up to the 97th, and the separation between them was 2 omega, and so on, and something like that. It measured was in 1993, very long time ago, and something like that. And they even observed these very big enhancements. If you have any question, please just raise your hands and interrupt to me. Now I will explain the three-step man model or the simple man model mechanisms. In the first step, what we observe is that the electric field reached the maximum of the laser field and bend the potential in such a way that create a barrier. And then the electron can tunnel out through this barrier and get ionized through the tunneling processes. And then the second processes, the electron is accelerated by the driving field here, as you see, and they gain energy from that laser field and turn back again to its ions core in this area of this region of the laser field and crash the ion core and recombine and emit the excess of energy as a form of XUV photons, as here is demonstrated. This has some kind of peculiar cutoff that I wanted just to mention because I will be mentioning that the relation with the comparison between the cutoff in the high harmonic generation and the cutoff in solids in a few seconds. And then here you see the cutoff is depending on the E amplitude to the square of the laser field strength and the wavelength square of the driving laser field plus ionization potential of the system in the atomic cases. So let's talk about what about ultrafast science in condensed matter physics. This is what the main topic of this talk will be. So in this talk, basically speaking, the top panel present the experimental setup that usually they use it. This is kind of mimic experiment setup, and this is the laser field. This is the material, and in this case is zinc oxide, and this is the grating that this is dispersing all the frequency, and this is the measuring the detector which is measuring all the frequencies in this configuration. And then here are the parameters of the laser field that were used, 3.2 microns around, and the intensity 5 × 10⁶, and with some kind of electric strength of 0.6 watts per Armstrong. And here you have the intensity of the laser field against the harmonic order. It's not seen very well because it's very tiny, the letter, but it is what it is. And the first spectra that they observed is a 0.52, and the second is in green line, as here you observe. And the second spectra is in 2.663, as here you observe in this hint. One fact to remark in this talk is the cutoff. The cutoff is for lower energy of the pulse is about 17th order, which is for solid a little bit high intensity plot, high intensity, high photon emission, sorry. And here in the second one, you have the cutoff, which is at 25 order. And then this is very huge in this case. In this panel, we can see the cutoff energy for different intensities or different laser field strengths or energies as well, if you wanted to want it. And then we see a linear cutoff dependencies which is not seen in gases. Remember that in gases, there is a quadratic scaling, and in solid there is now a linear scaling of the harmonic generations as a function of the electric field strength. This is the new things that was discovered in this paper of Chambu of 2011 in more than 20 years ago, sorry, more than 10 years ago now. And here you can see the crystal orient angle as a function of the harmonic order. And you see even harmonic here. This means that the symmetry is breaking of the system, or the inversion symmetry is breaking of the system of zinc oxide. So let's continue with the mechanisms in gases, and I explained it already, but I will explain once again to remind you that the mechanisms, and then I will explain the mechanisms in solids in a form of pictorial way. In the real space, the electron is tunneled out through the barrier, and then it's accelerating. It's a second step, and is recombining and crash the ion core and recombining. In this recombination, the electron emit that excess of energy that accumulates due to the laser field. Something similar is described in the momentum space for the atom. This is the real space. This is the momentum space. It's the same description, but in different spaces. The first one is in real, and the second one is in momentum space. Here in momentum space, we have the ground state. The ground state spectra is only one energy that is put here, and then here is tunneling out to the continuum spectra. The continuum, in gases has a parabolic relationship. And as a second step, there is an acceleration of this electron, which is excited in the continuum. And at some moment, when the electron come back to the ion core, the electron has the chance to recombine with its remaining ion and emit the excess of energy as a form of high HUV photon energy. And in the mechanisms in solid or semiconductor, here is a part of the real space. Here we see a periodicity, that this is one of the main difference between high harmonic generation in gases and high harmonic generation in solids. And here you observe when the electron is tunneled through the barrier, the formation of the periodicity make some block oscillations in the system, and between the lattice constants, which is demonstrated here in this green line, is the lattice constants, and the electron is excited to another from one localized binary state is excited to another localized binary state, and recombine gain energy and recombine it and emit energy in terms of XUV photons, as here is drawn. So this is a prototype of the Vanier block approximation, which try to recreate the potential part of the high harmonic generation from gases. This is very similar, that in gases, but it's not equal. In the momentum space, the description is more simple. In the position space is the interdipole matrix elements is just excited through tunneling the first step, then from the valence bands to the conduction bands, and then we create a hole in the band, and an electron in the hole in the valence band, and an electron in the conduction band. And then after that, the laser drive the electron backward and forward through this band, and at certain moment the electron can recombine as a third steps, and emit the excess of energy as a form of high photon energy, as you already observed from the experiment in zinc oxide from Shambu. So now what about nonlinear optical spectroscopy for proving topological states? Now this is one of the incoming field that is, or this subfield that is getting very popular. We get some ideas, and then I will explain from where we got some ideas. Here, what we have are different quantum Hall effects, and the quantum Hall effect, the quantum spin Hall effects, and the quantum anomalous Hall effects. And then I will be in this region explaining the three-dimensional one, not the two-dimensional one, because this is the material, and this region, the quantum Hall effects too. Inspiration. We get inspired by the experiment sometimes, and this is one of the inspiration that I got from the experiment of Chambu and David Reyes. And what inspired me? What inspired me is that MOS2 is a crystal which has inversion symmetry breaking and has a very curvature. And as a result of this very curvature, also you can, as a result of this inversion breaking symmetry, you have the very curvature in the system. And which is very interesting is that I was thinking in that moment is the very curvature is implicitly in the system. Can the topology be affect the high harmonics? This was one question that I raised to Maciek, and Maciek liked the question, and then we started to investigate from a theoretical point of view what is the implication of topological material in high harmonic generation, and how we can extract information from topological material in high harmonic generation. How is the time? How time I have? I forgot to.
You are okay. You are 25 minutes in, so you're good.
Okay, then here you can see the harmonic spectra produced from MOS2, that you have odd harmonic, you have even harmonic, we have odd harmonic, we have even harmonic, and so on, with the 10 and 11, 12, and 13th. So this is a result of the breaking, the even harmonics show up in the perpendicular direction with respect to the crystal orientation axis, and this is a result of the breaking of the inversion symmetry. And then let's talk a little bit the state of the art in topological high harmonic generation. In the first one, the first paper was introduced by Dieter Bauer. Dieter Bauer did one-dimensional calculation of TNDC, or or TDDFT, the time-dependent density functional theory, and in the SSG model. In the SSG model, we have a line which paired potentials of paired atoms here, and also we have with phase B, phase A, all the atoms are together joined. In the phase B, there are atoms left here without parent, and he does calculation for the phase B, which is the phase of topological. This is the phase of topological, and the phase A, which is this one already explained, and the phase B, which is already metal, because they can simulate it in meta. What they observed is a huge enhancement, and here that you see for the topological phases. Here is where the physics of topological state in high harmonic generation started. The other review, or the other paper that was published was by Misha Ivanov group and Ruiz Silva, where they observed a high harmonic generation with the helicity, and they proved the phase transition in Haldane model. I did also the same, but I will explain it. Since this is my talk, I will focus in explaining that part a little bit in detail. We published this paper in Physical Review B as an editor suggestion, and it's attracting the attention of people. It has like 100 citation in this, which is not too many, but it's more or less good. So let's start with the topological Haldane model postulates, or let's say statements. Haldane realized that the quantum Hall effects breaks the time reversal symmetry. This is a very important point here, because that still there are materials that break inversion symmetry, but only using the external magnetic field. Still, the Haldane model haven't been realized in the community of condensed matter physics, but God give the keys example of topological system. The other thing is that he analyzed the topological phase transition taking place to observe the quantum Hall effects without magnetic fields or Landau levels. The other thing is that they will explain what does mean topological phase transition in the next slide. In this picture is just the quantum Hall effects explained, where in the middle we have the magnetic field applied, and we have the spin charge current coupled at the edge of the system. And here in this plot, I have the resistances against the magnetic field here. And in the most interesting part is that this is the Hall voltage, and this is the parallel voltage realizing at the level of for this system. Here we realize that in nu, this is a quantum number, which is related with a quantum wave function, and the topological protections of that system. This number is discrete, is in terms of 1, 2, 3, 4, and something like that. We will describe a little bit later what it is. So Haldane model in Chern insulator or Chern number for that. Here we have the conical lattice of Haldane model, and then in the conical lattice, here we have the local potential in issue 1, to explain it very well. In here we have between the red and the blue, we have a hoping parameter. The hoping parameter is called T1. Between blue and red, we have a complex phases that here, complex phases or complex hoping parameter that here you can observe. It is the main, that will be the main source of breaking the time reversal symmetry, as I told in previously. This is the Hamiltonian of the Haldane model. Unfortunately, I don't have time to go into the derivation of this one because this take long time, and then I cannot present the other part of my talk. And then here there are the components of the Hamiltonian. The component of this B vector is for 1, for 2, for 3, and this is the Pauli matrix of the system. And here is where I wanted to explain the topological phase transitions. Just focuses in this is the so-called phase diagrams, and the phase diagram of Haldane. This is the local potential divided by T2 as a function of the phase phi. The Haldane phase diagrams is constructed by calculating the topological number, which is the Scherr number. Here is the definition of how it is calculated in terms of the flux of the Berry curvature, of the flux of the Berry curvature in the balance bands, or in the bands, or in the conduction bands. So here we can trace a line, an horizontal lines like that, and then we will observe that there is a Scherr number 0 here in this region. Then when we move on the magnetic flux phi, we observe that the Scherr number changes from 0 to -1, and this is here where the first topological phase transition happening. This is what I mean with topological phase transition, the changing of the Scherr number while we change the parameters of the phase diagrams. And then here we have another change from -1 to 0, from 0 to +1, and from +1 to 0 again. In this way, I can just explain it. This is technical details of how the Berry curvature is calculated. The Berry curvature is calculated through the Berry connections. The Berry connection is coming from purely the wave function, as here you can see, of the block wave functions, as here you see, and that is how the Scherr number will rise up or they get connected, and that resistivity, how is calculated in terms of this Scherr number 2. Let's go to the first result on linear and circular drivers. Here I will explain it in the linear case. In the linear case, here you have the linear, here you have the circular polarized light to drive the system. The system will be, this is a code that be carefully with this code to don't confuse or miss that the top part with the bottom part with respect to this red brown line. Here the top is related to trivial material and the bottom one is related to the topological material, and so on. And here we will have the output of the photons. First, we shine with linear polarized to see if we observe great difference between trivial and topology, and we will see that there was not such a great difference between them. Here there we have the harmonic generation spectra as the intensity as a function of the harmonic order. And here for trivial case in blue 1, and here for topological state in red 1. We observe an enhancement of that topological state, but the enhancement is not so great that we can claim that can be observed at experiment or something like that. That was we discard to study the topological phase transition with linear polarized, like, but Misha and the collaborator realized that this can be another way to analyze the pseudo-ellipticity and get information of the topology through that one. So in the second part is coming here, the topological case with circular polarized laser. We can observe that the intensity of as a function of the harmonic order again, and we can observe that from trivial case and topological case, trivial, remember, is in blue and in red the topological. We can observe between them a huge difference of of 4 order of magnitude when it is shined by the circular polarized laser field. This is really, really interesting and pushes out our attention in the study a little bit more what happened in the topological phase transition. As I explained it before, what is the topological phase transition? That's the model. So to study the topological phase transition, what we do is that in the shine the system with left circular polarized for the trivial phase, and for the non-trivial phase right circular polarized. But we do it from both shine the system with left and right circular polarized for trivial material, and the same things for topological material. What we observe here is a harmonic spectra as a function of the harmonic order, and the circular dichroism is in yellow area that here you can observe. What the circular dichroism is defined is nothing else than the difference between the intensity emitted for the harmonic nu with right circular polarized minus the intensity emitted with harmonic nu with left circular polarized driver. That is why here is in red left circular polarized driver, and in blue right circular polarized driver. That difference in the trivial phase is negative, but in the non-trivial phase, the topological phase, is positive. This means that they are totally different. This means that if they are totally different, we can use have the hope that we can use the circular dichroism to map the topological phase transition. And here I show you that topological measurement of the topological phase transition. In this mesh, this is the simulated data, and this is the phase diagrams of Haldane model. Here in the horizontal line, you can see the topological phase transition of this region, and here you can see the topological phase transition of this region too. In the region where the shell number is 0 is not completed to 0, but it is because of the oscillation that the circular dichroism is quite is quite sensitive to the the modification of the material. This is one code. This is for one code along this direction. Just let me explain again to see if this is not well explained. Here is we take the line along the magnetic flux phi naught axis, we will observe that we should map this kind of map phase diagram. And here in this region, green region, the Chern number is equal to 0. But in our case, it's not exactly to 0. The average is trying to be 0, but it is not. And then past, what is important is when we pass, we observe that there is a abrupt change in the circular dichroismos, as here you can see in the red line, and in the other harmonic 10, 13, 16, and 19, and so on. Another way to verify this was that we make a cut, vertical cut, here between the line J divided by the line JQ here as a function of the local potential divided by the T2, the second Hoping parameter. And what we can observe here is that there is there is a plateau again, and there is a region where it is oscillated, and there is a region which it goes to 0, the topological phase, the circular dichroism. So then we can conclude from this plot that the circular dichroism can map topological phase transition, at least not can retrieve the absolute values of topology or the Chern number. So let's go and move on. What about nonlinear optical spectroscopy, proving three-dimensional topological insulators? The Chern insulator was what already explained, or the Haldane model. The Haldane model is a Chern insulator because it has a Chern number. And then here, topological insulators are very different from Chern insulators because they have a C2 classification where this has another meaning, and then this is why it's called a topological insulator. Just let me clarify that one. And let's see here, this is the experiment in Bisno-Selonai, and the experiment is that has this setup, that have the setup of have this laser which will change the ellipticity from linear to circular polarized. And here is the rhombohedral structure of Bisno-Selonai. And here we can see the harmonic emissions from the system. This is basically speaking, or the detector that will detect this system. I will start with the results. The results is unique anomalous ellipticity in three-dimensional topological insulators. Here, the results is that we have the normalized intensity as a function of the ellipticity of the driving laser. The ellipticity, how change the width of in this direction of this cartoon of the circular polarized light. So what we observe here is that in that linear polarized, when the ellipticity is equal to 0, we observe almost the minima of the distribution of the harmonic order along the ellipticity, which is quite contradictory with the gas phases, because in gas phases, what we observe is a maximum in linear polarized and a minima in circular polarized, because the electron excursion is inefficiently in the case of circular polarized, because it's putting the electron go out from the ion parent. But in solids, it is a little bit different because electron is distributed through the lattice. I can recombine in whatever side of the lattice is if obey the quantum mechanical laws. So in this case, we observed it, this one, which was peculiar. We didn't understood very well why we observed that kind of anomalous effects that give us against the minima at 0 and the maxima when it is 1 or when it is circular, right polarized or left polarized. And for the theoretical calculation, what we observed was we have the capability in the theory of split the surface state from the bulk state. What we observed for the surface state is this line that you see here is following the trend or the tendency of the circular polarized light and so on. But the bulk state is not following that, it's following the normal behavior of the harmonic generation in gases or in solids. For instance, in solids, in MOS2, here you have the intensity normalized or the harmonic intensity as a function, normalized as a function of the ellipticity. Here we see some normal case or usual case, what they would say in a normal case, that where when the laser is circular, the emission is minima, and when the laser is linear, the emission is maxima. And here we call it extreme anomaly in comparison to the trivial MOS2 material, as here you can see in this one. And then we can say that topological surface state governs. Why? Because this is the surface state that is describing mostly that part of the experiment. So let's see the bulk state or the mechanisms that there is behind that. It is a little bit complex to understand all of these mechanisms, I know, but I will try to close it to you. So yeah, diagonalizing the resulting Hamiltonian yields that eigenvectors and eigenfunctions and of the bulk states. The spectrum is double degeneration as consequence of the combined action of inversion symmetry and time reversal symmetry. I have to say that topological insulator are protected by the time reversal symmetry. This is a very important concept here. And this is the energy spectra of the bulk state, and this is the eigenvector of the bulk state as well, which are double degenerated as well, and in form spinors, as here the two eigenvector can be considered as a spinor here. And here I show you the bulk state and the surface state of the energy band relationship, and here the spin texture. The surface state are calculated also by breaking the inversion symmetry of the rhombohedra along z direction. Here you have the breaking the Hamiltonian of the surface state, and from this Hamiltonian of the surface state, you can see that there is a transition in the z direction. There is a break in the z direction of the symmetry of those business cell on I. This is because we cut the business solenoid in a plane along the set directions, perpendicular to the set direction, and so on, to explain what happened in the surface, because it's the surface. Here is just the equation of motions and to calculate the density matrix, and also the definition of the intraband current and interband current. And here, as you see, here is the interband momentum and the interband density. And here you see the density matrix evolution equations. I will not go into the detail because it's too heavy for that. Let's go to the mechanisms which is encoded by the dipole matrix element. Here we have the dipole matrix element plot in hot plot, and we have the rotation of the dipole matrix elements vectors, and we have here, which is just a circular polarized. When the circular polarized is shining, the business solenoid is more coupled the circular polarized to the dipole matrix elements, in comparison when we have the linear driver laser. Here, in particular, what I want to say is that there is some two quantities, which is a spin out polarization out of plane, and a spin in the plane when you have, and a spin out of the plane that we have in this material. What here we have is that we were suspecting that the spin out of plane and the spin in plane might be related with the information of topology, and also is related with the information that we can read from high harmonic generation. And it was like that. These two quantities are related with the topological system. This here, as you see, we have the harmonic spectra as a function of the harmonic order, and as a function of the ratio A12, A14. And then when the ratio A14 for a reference is normal, this is that blue, this one that you can see here with the pointer. And when it's 30, you can see that this is very huge. There is the red one. There is very huge enhancement in the high harmonic generation. And when it is low, let's say low here is 1.6, it is green. The green is very low here. The spectra is very, very low in that case. And this is also demonstrated from here, from some mathematical analysis, the dependencies of the harmonic spectra as a function of the out of plane spin polarization, and in P related with the in plane spin polarization again. Out of plane, this means this in the set direction, and in plane means that it is contained in the plane of the system. And here is just the surface topological surface states, that you can see that this is a Dirac cone, that there is no gap in the bulk state, in the surface state, when the electron is ionized. It can be passed from the valence bands, the conduction one, without much effort. And finally, to conclude, let me say that we have proposed that we have the proposal of a chair insulator to test topology with the circular dichroismos. We already observed the harmonic generation from three-dimensional topological insulators as binuclear lines, as here I can draw you. And the separation of the response from the surface state based on symmetry properties and details theory based on semiconductor block equation that includes Berry phase, enhancements of the harmonic for circular fields related to vortex structure and high order unwrapping. So the outlook that the future that we want to investigate is that high harmonic generation could prove trivial and topological phase transition. This is already investigated in one's Nature Photonics that Chambu published, I think, during this year. Novel platform to study the driving dynamics of Dirac fermions. This is another line that have not been studied yet, and more precise, more predictable theories considering surface and bulk couplings and well higher light conduction bands is desirable. Wave semi-metal control and manipulation of Fermi arcs and monopoles, quantum spin liquid system, and Majorana modes in Kita F model. These are one of the topics that we were thinking can be studied in the future. So just let me acknowledge to my collaborator, here David Reyes, Denitsa Bekosheva, Chambujimir, Denitsa, David, Professor Donon King, my student Dasso that already graduated just yesterday, the group of Maciek here, and the guys Alex, which was helping with the Haldane model for doing that one. And finally, Richard Feynman view about teaching. Teach your student to doubt, to think, to communicate, to questions, to make mistake. Why not mistake? Because we can learn from their mistake. And most importantly, have fun in their learning processes. So thank you very much for your attention.
So thank you so much for your talk. We hope we have learned a few things today, also concerning solids and all the
I
rest.
hope so.
No? Other questions, comments? I mean, it's late in Korea, we know that. And we are happy that some people from Korea have also joined today. Please either raise your hands or put your questions in the Q&A tab. Anyway, what do you think is the next challenge for harmonics in solids from your perspective?
From my perspective, there are several challenges to see what would be the applications of high harmonic generation in solids. From my perspective, the other thing is that new quantum materials will be the next generation or the next phase to exploring high harmonic generation in solid, because quantum material are not including only topological material, including material like Eta F model, like topological insulators, the topological insulator with different phases, and so on. To see is really high harmonic generation can contribute something to the spectroscopy of the material in solids state, in particular in topological material.
Okay.
This is what I think.
Yeah, thank you. Now, one question for people who are really ignorant on that, including us. you talked about the topological phases and the trivial phases, and you showed some results of spectra where you could really distinguish what was going on. Can you explain to us what would make a topological phase and how would you recognize a trivial phase?
What the definition of topological phase is that we pass from one phase, which is trivial in the sense that doesn't have a whole conductivity or a whole effects, because that's the topological invariant in this case is zero. I will refer to Haldane model, but if the topological invariant is not zero, we can have a whole current, and this is what it is interesting, why it's interesting, because you can have a whole current without an external magnetic field, and this is what defines the topological material. Thank you for the question. I'm looking forward to hear more.
Yeah, I mean, so far I'm asking the questions, but everybody should feel free to ask some. So I don't know why people are quiet today. Sometimes they are. Is because I was wondering, I've seen many times that people sometimes they're calculating things around exceptional points, and then they circle the exceptional point, and then they get something that doesn't matter, or when they do this, they get some phase differences that have physical implications. But I've never worked on solids, so that's why I wondered, is there a connection somehow? No? Yes? Maybe?
Maybe.
Okay.
Can you repeat the question again?
You know, when you have, for instance, singularity, some points that is exceptional, and you circle around it, you're calculating something, and then you circle around it, and and you see
Yes.
that your wave function doesn't change, or your wave function picks up something.
Okay.
And then
Okay, you're
sometimes it
putting
has
more
some physics
fundamental.
too. Yes.
In this case, the wave function is changing as well, but the wave function in a pass, in a adiabatic pass, in this is more than talking about how the model it keep the same, and then if we make a pass, let's say circular pass in the BN1 zone, it keep the same and so on, and basically speaking, keeping the same path. What I wanted to say is that the path has to be slowly deformed in that region, and this is slowly deforming in one region, you have a path.
Okay. Yeah. All right. Would anybody like to ask something? I see there are a few people around. If not, let's give you the chance to ask the questions off-site. So we are stopping our streaming and we're stopping the recording. You can talk off record. So for those watching on YouTube, thank you so much for joining. And let's thank also Professor Chacon once more for giving his talk, and hope to see you soon.